No, that's fine. Just have him take 2 of them and call me in the morning. Bye. All the discussion about this cell phone stick-on gizmo and radiation and all the rest of it has led to videos being made by doctors. Now, apparently, the one in the last video was board certified. I'm very seldom bored, but I am certifiable, certainly. I want to answer a bunch of questions that were asked in a recent forum post. Now, the questions themselves appear below this video, further down the page, and I will read each one out, so you don't necessarily have to refer to them specifically, but they are there if you want to make sure that I'm reading the questions as they were written. Now, Ian asks, are you saying that the articles that Yaku posted at the start of this thread are actually rubbish? The answer to that is no. Question 2. If, as you mention and show, that the signals from the cell phone are deflected away from your head, what about the person sitting next to you? Are they not affected by these signals? But you did show us that when you removed the radio there was no noise. Then I ask, how does the signal get to the cell phone tower? Could some of it possibly be powered through the person standing next to you or on the path between you and the cell phone tower? And that's a very good question. What I need to do first is just explain a concept known as the inverse square law, because it's very important to this particular discussion. If we go back to my analogy using the light bulb, consider the light bulb has a filament in it. The filament is really just a length of wire, and when an electric current is passed through that wire, it glows white hot and gives off the light that we see and we use. Now, the light bulb is not quite spherical in shape, although if we look at the sort of the bulk of it, the top part, it's pretty close to being spherical, and that suits my particular illustration. Imagine, if you will, that this glass, instead of being clear, was frosted. If we were to switch the light bulb on, then the light emitted from the filament would illuminate the surface of the glass. The glass would have a sort of white color to it, and it would light up very brightly. I'm sure you've all seen frosted light bulbs. Now, the amount of light given off by the filament in this light bulb is a fixed amount of light. It is measurable and quantifiable. Now, all of that light that is generated strikes the inside surface of our frosted glass bulb and illuminates that surface. So as we look at the bulb when it's switched on, we see this white sphere which is very brightly lit and radiates light. It's not quite white light, but close enough. If we were to take the surface area of this little sphere and draw lines around it, much like the lines of longitude and latitude that you see on a globe, if we were able to position those just right so that each little square on the globe was 1 square centimeter in size, then we could add up the number of square centimeters around this globe, and let's say, for the sake of argument, that it worked out to be 100. I think it's probably a little bit more, but it doesn't matter. Let's say there are 100 square centimeters on this surface. All other things being equal, if there are 100 square centimeters, then 1% of the total light output from the filament will be focused on each of those square centimeters. Okay? So the filament gives you 100% of its available light. It's spread out over 100 little squares, so each square is receiving 1% or 1/100th of the amount of light given off by the globe. If we were now to take this globe, okay, now we go back to a clear globe again, and we were to put it at the center of a beach ball. What would happen then when we switch it on? Let's assume the beach ball is white, much the same as our frosted glass was. What's going to happen then is that the same defined amount of light from that filament is now going to keep moving outwards, further away from the filament, until it strikes the inside of the beach ball, and it's going to light up the surface of the beach ball. And as we look at that beach ball from the outside, we're going to see this brightly lit white sphere. If we now start drawing grid lines on that beach ball, again, so that they are so that the squares are 1 square centimeter in size, we're going to find that whereas our light bulb has about 100 squares, the beach ball is going to have perhaps 1,000 or 10,000 squares. I haven't done the maths. It's not important for the sake of the illustration. So now what we have is we have that same amount of light radiating from the filament and striking a far greater number of square centimeters on the surface of the globe. So whereas here it had to illuminate 100 little squares, on the beach ball it has to illuminate perhaps 10,000 little square centimeters. So each square centimeter, instead of getting 1% of the light, is now going to get a small fraction of that. So the amount of light energy per square centimeter on the beach ball is minute compared to the amount of light per square centimeter on the frosted globe, simply by having moved away, because the same amount of light now has to be shared over a greater surface area. And the further away you move from the globe, the bigger your sphere becomes, the smaller amount of light, or the weaker the light signal, the weaker the light radiation is per square centimeter on that surface. Now I hope that illustration makes sense. We're comparing the surface area of the globe to the surface area of the beach ball, and if you move further away and you have a bigger ball, the same thing applies. Now the interesting thing is that let's just look at this globe, for example. The surface of the globe is, well, it's not equidistant from all parts of the filament, because the filament is a sort of curved line in the bulb. It isn't one little dot right at the center. But if it were just one little dot in the center, to simplify the maths, we could measure from that dot out to the surface, and we would find it would be about 3 centimeters. Okay. Now if we were to move away from the globe by another 3 centimeters, in other words, we double the distance from the source of the light to where we are. Over here we're at 3 centimeters, we move away to 6 centimeters. Instinctively you would expect the amount of light striking your hand at the 6 centimeter mark to be 1/2 of what it is at this point here. It is not 1/2, it is in fact 1/4, because of the inverse square law, and that relates to the surface area. And it becomes the numbers become very interesting and become quite big when we start talking about bigger distances, and in particular as it applies to cell phones. Now if we have a look at this, the antenna inside the back of this cell phone is roughly 1 centimeter back from the front surface. So the front surface of the cell phone that's against your head keeps the antenna away from your head by about 1 centimeter. I'm rounding the numbers off. It may be 9 millimeters, it may be 12 millimeters, but for the sake of the argument, 1 centimeter. If you take that cell phone away from your head and you put it down on the desk next to you, so that it's perhaps 1/2 meter away from you, 50 centimeters, because of the inverse square law, the amount of radiated power of radio signal that strikes your head from the cell phone when it's on your desk is 1/2.5 thousandth of what it is when it's against your head. Okay, let me explain how that works. If we start off with it against your head, where the distance from the antenna to your head is 1 centimeter, let's assume that at that point we're at the maximum power level. We can't really increase it any further because we can't get closer. So let's call that 100% power level. That's the most we can get at 1 centimeter. If we move the cell phone away from the head by 1 centimeter, then the distance, we've added another centimeter here, in other words. So the distance from the antenna to the surface of our head is now 2 centimeters instead of 1. Now the inverse square law works simply by squaring the distance and then dividing that into the amount of power. So for argument's sake, when we have 1 centimeter, 1 squared is 1. So we have 100% power divided by 1 is 100%. So that's our reference. When we move it away, and we're now 2 centimeters between the antenna and your head, 2 2s are 4, so we divide the power by 4. Hence, moving it 1 centimeter away gives you 1/4 of the amount of power going into your head. Once you move it away and you put it on your desk and you're 50 centimeters away, 50 times 50 is 2,500. So the amount of power being radiated from the cell phone is now expanding outwards, okay, in a sphere. This is how can I put this? This is really mathematical. The cell phone doesn't in fact radiate equally in all directions, but the inverse square law still applies, and the analogy of the sphere is still applicable and still very useful to visualize it. So our little sphere that was 1 centimeter has now grown to 50 centimeters. So the surface area of our sphere is now 2,500 times greater than it was when the cell phone was right up against our ear. Which means that simply putting the phone down on the desk in front of you and using it in hands-free mode will decrease the amount of radiation that you are exposed to from 100% all the way down to 0.04%. That is the total amount of power divided by 2,500. Now, to get back to the question about the effect that using your cell phone might have on somebody sitting next to you. If I'm using the cell phone and I have it up against my ear, as I showed in my previous video, most of the radiation is directed away from your head. And as Ian asks, what happens if there's somebody sitting right next to you? Aren't they then exposed to that radiation? And the answer is yes, absolutely, they are. But the distance from the cell phone to their head next to you is probably somewhere in the region of half a meter at least. If you were sitting side by side with somebody on a bus, for example, if you were really squashed together cattle class on an aeroplane, the distance may be slightly less, but it's unlikely in practice to be really less than about half a meter. And in practice, if you were sitting next to somebody in a restaurant or at a boardroom table, the distance between your head and the head of the person next to you is probably closer to 1 meter than it is half a meter, because our personal space dictates that we sit a certain distance apart. But in any event, whether it's half a meter or 1 meter, the point is that the inverse square law applies, and that means that yes, while the radiation from your cell phone does indeed strike the person next to you, it is only a minuscule percentage, 0.04%, possibly less, of the total radiation is actually going to hit that person. The rest of it is radiating away in all other directions and going all over the place. The amount of the radiation that does hit the person next to you is going to partially be absorbed by their body, and as far as anybody can tell, that normally means that it gets converted into heat energy. That's exactly the way that a microwave oven works, for example. You bombard it with high levels of radio frequency radiation, microwave radiation. And by the way, the term microwave simply refers to the physical size of the radio waves or the frequency of the transmission. Some of the energy will be absorbed, probably converted to heat. Some of it will be reflected off that person. It'll bounce around the room, it may bounce off other things, some of it will escape the room and carry on its journey until it reaches the cell phone tower. My point is simply that while other people around you will indeed be exposed to radiation, the amount of radiation that they're exposed to from your cell phone is very, very small compared to the total amount of radiation that is emitted by the cell phone. Ian's next question: if the antennae are built so precisely as you depict, does the cell phone tower always have to be on the side that is away from you to pick up the signal? So how do two people sitting next to one another listening on the left and right ear pick up the signal? So what Ian is asking is, if I'm using my cell phone and the signal is being radiated off that way, how does that work if the base station is in that direction? Or if I have my cell phone on my left ear and the person next to me has it on their right ear, then we're radiating in two opposite directions. How does that work? The answer is that the signal that emerges, that is radiated from the back of the cell phone, is not coming out in one very precise line like you would expect a laser beam or a jet of water from a hose pipe. It is kind of spraying out in almost every direction that it can, other than out the front of the phone. So when it's against my head like this, a minimal amount is radiated towards my head. There is definitely some that still radiates towards the head. They cannot design and manufacture an antenna, especially in the small space that they have, in such a way that there is zero emission towards your head. But the bulk of it moves away in all other directions. So it's up, front, back, down, off to the side. Not only that, but that signal will then bounce off all manner of things that might be in the room, especially anything that's metal. Once it gets out of the room, it can bounce off other things that are outside. Certain what's the right word? Certain flora, trees, things like that contain a lot of liquid. In some instances, depending on the frequencies involved, they will reflect a signal. In other instances, they will absorb it. But the point is that signal doesn't just come out of the cell phone and go off forever and ever and ever in one straight line. It scatters all over the place. It's just that at the beginning of its journey, where it's at maximum strength, right at the cell phone, the designers of the cell phone have done what they can to ensure that it radiates as far as they possibly can away from your head and not into your head. Next question, Ian says, from your explanation, the cell phone tower obviously is only sending the signal in your cell phone's direction, otherwise you would not receive the signal. So how does everybody else facing a different direction get to use their cell phone? Or is the signal emitted as you first described that it is not doing, like a light bulb? Okay. So Ian's asking if the cell phone base station emits a signal, is it highly directional? Now, there are two parts to this. First of all, if you were to take, I need something to represent a base station here. Let's use this pen. If this is our cell phone tower, and you'll see this if you go out and look at almost any cell phone tower, certainly those in any built-up area, you'll notice that the antennas are actually arranged in groups of three. What happens is if we were able to hover in a helicopter over the top of the cell phone tower, looking down on it, you would find that there are three antennas, okay, arranged at 120-degree intervals. The idea being that the geographical area around the cell phone tower is divided into a pie, kind of a pie shape, if you like, with each sector being 120 degrees. And the reason that they do that is to increase the capacity of the cell phone network, so that each 120 degree wide sector can be addressed independently by one base station. So you can have multiple people in a geographical area all sharing that same base station at the same time without interfering with each other. It's a little bit like being able to have 3 separate base stations but all located in one point, facing slightly different directions. If you are within one of those 3 wedge-shaped areas of that base station, then in much the same way as, let's look at something like the headlight on your car, where the light is aimed away from the vehicle in front of you to light up the road. That is what happens with the signal from those antennas on the base station, except it's a little bit wider than the lights on your car. So it spreads out over about a 120 degree angle. And as long as you are anywhere inside that, the signal is going to reach you, and the signal will strike your cell phone. Now, in theory, if the face of your cell phone was aimed precisely at the tower, you would compromise the signal. But that's if you're out in free space where there's nothing for that signal to bounce off. In practice, what happens is that the signal arriving from the cell phone tower is bouncing all over the place. It's bouncing off walls in the room, whatever objects there are, wires in the wall, pipes that are in the wall and the ceiling, any metallic objects in particular. So that signal, even if although it may arrive, let's say, through one particular window into the room you're sitting in, it's actually going to scatter all over the place. So it hits your cell phone from all directions simultaneously. It's a rather crude explanation of it, but that's how it works in order to overcome that. It's not designed like that to overcome the problem of the directional antenna. Radio waves just do that naturally, especially at the kind of frequencies that cell phones operate at. The waves will bounce off various objects. So the fact that the antenna in the cell phone is directional to some degree, certainly in terms of limiting the radiation from the front, the system as a whole still does work very well in spite of that. Next question: is the signal from the cell phone tower that weak because we do not hear the irritating noise as we drive by it? Then how do we communicate? The maximum permissible power that can be transmitted by a cell phone base station is somewhat higher than that is ever transmitted from a mobile handset, but it's still a relatively low amount of power compared to, say, a radio station or a TV station. And because of the inverse square law, unless you are physically close to the antenna, and by close to the antenna I'm talking about within just a couple of meters, then you wouldn't be exposed to the same amount of radiation as you're exposed to from a cell phone if you were to put the back of the cell phone up against your head. Or when I did my little demonstration with the radio, I had to put the cell phone right up against the back of the radio in order for the buzzing to be heard on the radio. The moment I moved it away, even 1 or 2 centimeters, the buzzing faded right away. And that is because, due to the inverse square law, as you move away from the antenna, the strength of the radiated signal drops off exponentially. So it becomes very much weaker very quickly as the distance increases. So driving past a cell phone base station, for example, you would never be close enough to the antennas on that base station for the level of radiation to be so high that it caused a buzzing sound on your radio the way that I did in that little demo. Certainly, if I took that little portable radio and I climbed up the cell phone tower and I got to within a few meters of the antenna, I would get that same buzzing sound. Is the signal noise that you demonstrated, in other words the buzzing that you heard from the little portable radio that I used, Is the signal noise that you demonstrated the only signal that is emitted by the cell phone, or is the noise you demonstrated one of the ones that you can pick up with the radio because it is in that frequency bandwidth which is as harmful as the radio signals for listening to your favorite radio, Soapy, on? I'm afraid I don't quite understand that question. Or certainly the first part makes sense. Is the noise that I demonstrated the only signal that is emitted by the cell phone? Now, that buzzing sound that you heard when I put the cell phone back to back with the radio, that is the primary transmitter in the cell phone, the main transmitter, which radiates by far the greatest amount of power. There's other circuitry inside the cell phone. It has a microprocessor to run all the functions, and the calendar and the clock and all kinds of stuff that goes on in the cell phone. And any computer chip that's busy running generates a certain amount of electromagnetic radiation. But without question, by a massive amount, the strongest part of the emission from any cell phone comes from the transmitter, which causes that buzzing sound that you hear. Now, there is other circuitry in a cell phone, in fact in just about any electronic device really, that creates and radiates electromagnetic fields of various different types, different frequencies, different strengths. Generally, these don't concern us because the strength, the level of the radiation created by those devices is so microscopically low that, as far as history tells us, there just is no way that can really cause any harm. We've been using electronic devices in our homes and around us just about forever. When I say forever, I mean in terms of our lifetimes. Since we were born, there have been radios, telephones, things like that around, and we've never concerned ourselves with those things, and I don't think we need to, purely because whatever radiation you do get from them is quite harmless. The radiation that you get from a cell phone is a relatively high level, and the critical issue is that we stick it right up against our heads, right next to our brains, with the antenna right there. And if cell phones were not designed in such a way that most of the signal radiated away from you, then it certainly wouldn't surprise me if we had already seen quite a few people developing tumors. Now, I'm just guessing here. I'm certainly not a medical person. I have zero experience whatsoever with what the radiation from a cell phone could do to the human brain. I only know that in broad principle, radio signals that are powerful enough can certainly cause a lot of damage to human tissue. And again, I refer to the microwave oven as being a good example of how that is used deliberately to cook meat. And of course, the fear that people have is that the radiation from a cell phone might do the same thing to our brains, even if it takes longer than a microwave oven would. And I don't know one way or the other whether it does or doesn't. My expectation is that the radiation from a cell phone does have some effect on us, some negative effect, some damaging effect on our tissue. And it certainly would not surprise me in the least if various studies came out over the next several years showing actual examples of people who had been monitored and followed over a period of time and had regular, I'm not sure how they would do it, I suppose an MRI scan or something like that, perhaps at yearly intervals. But I'm not sure how you would do a controlled test, because you can't really you don't put people in cages like guinea pigs, and it's also very difficult to do tests like that over a great number of years. And the whole cell phone issue has only really been an issue for 20 years or so. Before that, we just didn't have portable cell phones. In this country, for example, it's only 15, 16 years, give or take, that we've had cell phones of a portable nature that you would put up against your head. Incidentally, the earlier cell phones, most of you will remember, had a little stubby rubber antenna sticking out the top, and in some cases there was an insert in that you could actually pull out to extend the antenna. Now, those antennas were what would be called omnidirectional. In other words, they radiated a signal equally in all directions. So if you had one of those up against your head with a little stubby rubber antenna sticking out the top, or the type that you pull out about this long, like a little flexible wire thing, very definitely those would be radiating a signal equally in all directions. And if you had that up against your head would be absorbing a healthy portion, probably somewhere between 1/3 and 1/2 of the total radiation from the cell phone would be going straight into your head. And I have no doubt that one of the reasons that the cell phones that we get today have antennas designed the way they are to try and make as much of the radiation as possible move away from your head is precisely because of the fear of the damage that potentially can be done to your brain from those. So I'm certainly not saying for one instant that claims of damage by cell phone radiation are bogus or nonsense. Far from it. And then Ian says, please could you show us from your well-equipped lab, as shown by the array of computer monitors in the background, the full spectrum of the frequencies emitted by the cell phone and where they are all going. As you have very ably shown us the harmless frequencies, what about the others? Well, I'll answer the question in the reverse order. The radio waves emitted from the cell phone that I was referring to in my previous video that caused the buzzing on the radio certainly were not called harmless by me, not at all. In fact, of all radiation that I can think of that may come from the various parts of circuitry in a cell phone, that radiation that caused the buzzing, in my opinion, would be by far and away the most dangerous, not harmless at all. It's certainly very much more powerful than any of the other very, very minor radiation that you would get from the circuitry. And definitely I wouldn't refer to it as harmless. The only way that it could be called harmless is if it never touches your head and never gets involved with your body. But if that radiation was going directly into your head, I mean, if we were to turn the cell phone around and if I held it against my head the wrong way so that the signal coming out of the back of the behind the antenna of the cell phone was placed against my head and directed straight into my head, I would fully expect that to do real damage. I don't know how long it would take, but it's definitely not something that I would be about to try, that's for sure. So certainly I don't regard that as being harmless. As for showing the full spectrum, well, first of all, this is my office, not my lab. My lab is downstairs. It is very nicely equipped, and I do electronics design and development work there. The room I'm in now is my office, where I spend most of my time, and the monitors behind me are just my normal everyday computer monitors. There's nothing fancy here. As for showing the full spectrum of the cell phone, the spectrum analyzer that I have and use regrettably is incapable of monitoring the digital transmissions of the type used by employed by cell phones. So I'm afraid I can't actually show that to you. I will see if I can find some information on the internet about that, though. But I don't really think that it's particularly important. And why I say that is because we have the main signal coming out of the back of the cell phone. We already know exactly what the spectral components are of that signal. We already know that that signal has the potential to do damage. So that is not actually in dispute. Having a look on a spectrum analyzer that might reveal other signals at perhaps 1,000th or less of the intensity of that signal is not really of much interest. They're not the ones that cause the concern. It's that powerful signal that comes out of the antenna. That's the one we've got to watch for, and we certainly have to keep that away from our heads as far as possible. And then the final question, which I think I've already just answered: are there any other frequencies that may be produced by the cell phone that are not emitted by the antenna, but simply by the electronics of the phone? After all electronic components emit a frequency. Perhaps a better way to put it would be to say that after all electronic circuits, in other words, once you've put components together and formed a circuit, all electronic devices, shall we say, emit some kind of electromagnetic radiation. And yes, that's true. You could take a calculator, for example, and there are ways of detecting and measuring electromagnetic radiation from this calculator, but they don't concern anybody because the level of radiation is so incredibly low that it just isn't an issue. Bear in mind that we are surrounded and bombarded by all manner of electromagnetic radiation all day, every day, from a great number of sources, and not just in the last 100 or so years since radio was invented. I forget now the exact date, but since long before then. There are all kinds of things that cause electromagnetic radiation from the sun, from other planets, from the Earth itself. So, being excited about the fact that there is electromagnetic radiation around us is taking things a little bit too far. What we have to do is we have to find out what types of electromagnetic radiation are potentially damaging, and also how much of it is required to cause any damage. For example, as I sit here, there are radio stations in the general Johannesburg area transmitting signals. Now, I know that electromagnetic radiation coming off that transmitter from whatever radio station you choose is bombarding me right now. How do I know that? Because I can pick up a radio, switch it on, tune to a frequency of a radio station, and the radio will pick up that signal, resolve it, and I'll hear the music or the speech or whatever it is. But it doesn't concern me because the level of that radiation is so low that I can't imagine anybody thinking that would cause any harm. Of course, it could turn out that I'm wrong. It could turn out that even those very, very low levels do have some effect. Anything is possible, and history is full of examples of people who believed one thing and then found out later that they were proved wrong, but things in fact worked a different way. But certainly I think we have a good enough understanding of radio and the way that radio works to know that one needs to be exposed to a power level above a certain threshold before any sort of damage begins to occur. The primary problem with being exposed to electromagnetic radiation of the type that comes from, say, a cell phone is that radiation goes into your head and is absorbed and converted from radio energy into heat energy, which quite literally starts cooking the skin tissue or brain tissue or wherever it's going into your body. Now, your body has a way of liberating, getting rid of heat. The really obvious example is if you exercise and your body gets very hot, you sweat, air moves, sweat evaporates, takes away the heat, and there are various mechanisms. I think we all understand that our bodies can be exposed to certain amounts of heat and cold, and the body is able to compensate and deal with that. If your body is artificially heated by some external source, your body is able to cope with that. It's able to get rid of that heat, to deal with it in one way or another without there being any damage whatsoever. But if you were to apply too much heat in a short enough space of time so that your body wasn't able to get rid of it, you'd have a problem. Think of a bucket with a small hole at the bottom. As long as you're putting in very small quantities of water here and there, that bucket will never fill up. It'll be fine, because whatever you put in drains at the bottom. The bucket has a mechanism for keeping itself empty. But if you start pouring in enough water at a high enough level, fast enough, possibly from multiple sources, you'll be adding it faster than it's able to drain from the hole in the bottom. The bucket will fill up and overflow. And that's an analogy for what I'm talking about. Our bodies do have the ability to cope with certain amounts of heat energy and the heat that may be caused by being exposed to limited amounts of radiation. But certainly once the level of radiation that we're exposed to exceeds a certain level, our bodies cannot process that and deal with it, and wherever that's being applied, to your ear or wherever it is going to start cooking. There's just no doubt about that at all. So the real issue is the amount of radiation from a cell phone sufficient to cause heating at a fast enough rate that our bodies can't cope with it? And if the answer to that is yes, then it's going to cause some sort of damage. Okay, I've gone on far longer than I anticipated, so I'm going to stop this video at this point.